Good day, everybody. Let's get started. This is calculus, and let's break back into section 4.3. I got down to homework three last question three in section 4.3 last time. This section can go on for a while, um, but in question three, state the x coordinates of the inflection points of the curve below, and this is the graph of just f right here. So there's no weird stuff going on. Now, what are we? The inflection points happen at around negative x equals neg 2 and x equals 0, um, or if not exactly, right, close to x equals neg 2 and x equals 0. So here and here. You go from smiling to frowning, frown. You just sort of have to eyeball it. It's a little harder to check. Uh, we're neg 2, you can kind of tell we're frowning for we're frowning for a long time coming in from the left here, but at x equals neg 2, we finally change over to smile. And then we smile for a while. We smile just for a little while, but then we hit the y axis, and past that y axis, we immediately go back to frowning again, and we stay that way. So this one is just kind of is what it is on part A. And yeah, and when I say frown, that's concave down. When I say smile, that's concave up. And you just sort of have to ballpark part A. And really, they sort of part B. The flat places are about at neg 3 and pos 1 and neg 1, right? In part C, you had to be careful because we have to reject neg 1 because you got to change from negative to positive, right? Like we said earlier, you got to pierce them through. Coming in from the left, we pierced up here, and then we pierce back down here. Okay. Now, number 4, consider the following function right here. Find the derivative. Well, just do the power rule and the sum difference basic rule. You'll get this. Find any critical numbers. You just set f prime equal to 0 and solve. That'll be where our slopes equal 0, right? And the x values that make f prime equal 0 are 1 and 3. Check it and see by algebra. And now find the intervals on which f is increasing. Do algebra 2, use a test point, but you'll find that it's this interval and this interval. You separate them with a comma. Find the intervals on which f is decreasing. Again, algebra 2, the interval test. Do this. Okie dokie. Find local min and local max, the y values. So what you'll do is, again, here, if you want to see all the gory details, here it is. Now you plug 1 into f, you'll get 2. That's your local max. You'll plug the x equals 3, the other critical point, x equals 3 into f, you'll get neg 6. And that'll be your local min. The critical points, they'll give you your local min or your local max, or they could give you a saddle point. Now, well, let's see. Number 5, we have something like this right here. If it does not exist, enter D and E. And something, well, back at this one. That's right. And we rejected. Touched and turned back around again. Back when y equals x cubed. This is, we're, uh-oh. I didn't tell you guys a lie, did I? I hope I didn't. Like if I did y double prime of, uh-oh. I hope I didn't lie to y'all. I think I used the wrong thing. Guys, I meant to say that was a saddle, not undulation. Undulation would have been, well, shoot. I need to edit the video. Darn it. So here's an undulation point. Undulation point would be y equals x to the fourth, not x cubed. X cubed gives you a saddle point. Undulation point would be y equals x to the fourth. This, by the time you guys get the video, I'll have this edited. And the trouble with an undulation point is we either keep frowning, we do not change our smile frown status. We either keep smiling or we keep frowning. Like in this case, we keep smiling, right? That's the trouble with y equals x to the fourth. So 0, 0 would be an undulation point, right? You can tell we never frown, right? In this case, in this example, we never frown, and that's a problem. There is no inflection point, and I'll make that correction accordingly in this video. I'll have to trim out. What I was thinking of with y equals x cubed, y equals x. What about y equals x cubed? That I was doing the wrong thing. I don't know why my brain wanted to do that. 0, 0 in this case. Is it an inflection point? I dare say that it is. It is an inflection point. That's not a problem. But what about 0, 0? 0, 0 is also a saddle point. It's the first derivative where we get trouble, not the second. 0, 0 is also a saddle point. So it's not a, notice obviously, right? It's the reason it's a saddle point is like your slope is positive to the immediate left and it's positive to the immediate right. That's why it's a saddle point. In particular, it is not a local min or max. It's not the most positive or most negative fish in the sea. It doesn't have either luxury. It's still a critical point, right? Albeit, don't get me wrong, x equals 0 is still a critical point. It's just we have a saddle point. It happens. Saddle points happen all the time. Yeah, you have a critical point. And you remember, f prime cannot exist and give you a critical point. Let me give you another example of a critical point where f prime does not exist. Let's do f of x or y equals absolute value of x. The origin, right? Now, we don't have concavity here at all. 0, 0, the origin, you can tell it is a, now obviously it is a local and global min, right? It is a local and global min, obviously, all day long. But now f prime f prime does not even exist. F double prime surely does not exist. But f prime of x, well, there's the graph. But notice f prime of 0 does not exist. But that's fine. That's one of the criteria. If you go back and look at the criteria for a critical point, just if you know that it works. So x equals 0 is a critical point. And remember about critical point, it is a point C comma f of C where, you know, where f of C obviously exists, and either f prime of C and either f prime of C equals 0 or fails to exist. That's a critical point, right? So yeah, you know, and at such points, at such a point, x equals c, well, what happens? We will have a local min, local max, or a saddle point. It happens all the time. But anyway, let's see if there's a juicy example where f prime fails to exist. Well, nah, that's all right. Local min max at a sharp point. Yep. I don't want to watch this whole video, guys, obviously, but let's just. So he's drawing that. No, that's smooth as a baby's bottom. I didn't want that. I wanted one that had a sharp. Here we go. Yep, there we go. Right here. At 5, 7. Yep, there's a sharp point. So yeah, sure. And the derivative would not exist there, but but f exists there, right? So we're fine. So coming on back. Now let's look at this function. So we have wait, before I do that, let me just come on back to Desmos. Yeah. So for the absolute value function, we have a local and global both minimum at the origin 0, 0. X equals 0 is the local min value, or the local min, and is the local min location. We refer to x equals 0 as the local min location. And of course, y equals 0 would be the local min value, just to keep the notation straight. And if we come over here to, now this is the saddle point, x equals 0 would be the critical value, or just the saddle point value, right? Would be the location of the saddle point. And of course, y equals 0 would be the saddle point value. And it's still a critical point, even when we get saddle points, right? And yeah, and of course, and notice if we let, guys, it is an inflection point. If we let f of x equal x cubed, and indeed, if you do the derivative, the double derivative, f double prime, by the way, that would be what, 6x? F double prime is this purple line, and it changes sign, right? It does what an inflection point is supposed to do. It either vanishes or fails to exist at the point of interest. In this case, it vanishes to 0, and it changes signs in the immediate vicinity to the left and right. We have an inflection point at the origin. So saddle and inflection. So yeah, 0, 0 indeed, sure enough, is a saddle and inflection point. Just to summarize. Yeah, it happens, right? Now this guy right here, now we can't really talk about concavity here. Yeah, we don't really, concavity doesn't really make a lot of sense here, because if we did the second derivative, we'd get 0 here and over here, and it doesn't even exist right here. We can even do the first derivative right here, heck. So yeah, we can't even do we can't really call the origin anything, right? We can't even do the first derivative there. We cannot refer to the origin as either as any kind of undulation or inflection point. It doesn't make sense. The derivative is zero on both sides, and the first derivative doesn't even exist. Indeed, f prime, the first derivative f prime of x, does not even exist at x equals 0, and that is a requirement. It's so the requirement we require f prime to exist, right? F double prime can fail to exist, but f single prime has to exist. So yeah, it's not inflection nor is it undulation. It's just there is no second derivative structure here. You're out of luck here, right? It's a barren land. So let me just come on back. Hope that helped. Now y equals x to the fourth. This is undulation, right? So this is, if you do the second derivative, you'll get y equals, or in particular, you'll get y double prime equals what? 4 times 3 is 12x squared. And you can tell to the immediate left and right, because of that square power, you'll stay positive. So this is all day undulation, right? Okay. And now what about and it's a local. What about in terms of that's in terms of y double prime. What about in terms of y prime? It is a local and global minimum, right? If you want to just look at the first derivative, the slope derivative y prime, yeah, obviously it's a local and global minimum. It's pretty there, right? So it's an undulation, a local and global minimum. You can get all sorts of garden variety things. So let me come back to Webb-Assan. Now here's F. Now to get the intervals of increase and decrease, you do the algebra 2 test point. You set F prime equal to 0 and you get your critical points. You get the x values that make F prime vanish. So you go down here, you do that, set that equal to 0. You'll get wherever the cosine and sine equal. But we only want to be on the interval from 0 to 2 pi. We don't want an infinity of things. So on that interval, pi quarter and 5 pi quarter. So we check those points out and we do our chop offs there. But we want a test point that's strictly between 0 and pi quarter, and another test point that's strictly between 5 pi quarter and 2 pi. Because on those intervals, F prime is positive, as you can check it in Desmos. That those any test point will betray the fact that the function F prime right here is positive on these intervals. And any test point but that's on that other interval between 1 pi quarter and 5 pi quarter will give you a negative F prime. This function right here will go negative on you. Okay, so because of that, because F prime is positive on these two guys, the original F is increasing. And because F prime is negative on this single interval, F is decreasing on that interval. And now F changes from increasing to decreasing at x equals pi quarter. You can check from looking at the graph, and ditto, it goes from decreasing to increasing at x equals 5 pi quarter. You look at the graph. So now, and furthermore, from the behavior, why should that make sense? That should make sense. It goes from increasing to decreasing because when we go beyond, notice at pi quarter to the left, we were increasing. To the right, we start decreasing. So this makes sense. Yeah, it better be that way, right? And analogously for 5 pi quarter and its stuff. So because of that, f of 5 pi quarter had better be a local minimum, because if you're increasing on the left and decreasing on the right, you're a low. Wait, so wait, they're doing. Oh, I need to be over here. Pi quarter. Yeah, if you're increasing on the left and decreasing on the right, you're like an upside down parabola, right? Y equals -1 times x squared. The upside down parabola. You're increasing on the left, you're coming up from the left, but you're falling down on the right. I didn't draw that one in this video, but I could draw it real easy. So that would be a local max value for 1 pi quarter. And indeed, to the immediate left, we're increasing. To the immediate right, we're decreasing here. So that's why it's a local max. Okay, local max. Yeah, you hit the pinnacle, the tip top of, like, for example, the upside down parabola, you'd hit the top. This is not the upside down parabola. I'm just using it as an analogy. The same idea. Now, if you're a local minimum, you're decreasing to the left and increasing to the right, like the classic parabola does, as an analogy. So this would be this guy right here. Plug this into the original function f, you'll get this. Plug this into the original function f, you'll get this. This will be your local min. This will be your local max. I've got to go soon. Now, f of x, number 6, f of x is this. Find the intervals on which f is increasing. And find the intervals on which it's decreasing. Find your local min and max. Guys, you'll do your f prime business, set it equal to 0, but x would have to be 6, right? Euler and x had to be 0 here, 6 here. E can never vanish. So that's going to be your ditty up on your interval. Just pick a test point between -infinity and 0, and that if that test point gives you a positive f prime, then you will be increasing, and if it gives you a negative f prime, you'll be decreasing. Okay. And we also need to look at the open interval from 0 to 6. We've got to do a test point for it. So as it turns out, f prime is greater than 0. So if f prime is positive, I need to be careful about something. If f prime is positive, it's the original f that's increasing. Take that home with you when you go home. And if the original f prime is less than 0, it's the original f that's decreasing. So if f prime is positive, f prime is positive when x is between 0 and 6. That means the original f is increasing. And if f prime is negative, f prime is negative for the extreme x's. So f is decreasing when x goes extreme, either in whichever direction. So the original f is increasing on 0 to 6 and decreasing on the extremes. Now, if you plug in x equals 0 in the original f, you'll just get 0 right here. And if you plug in f like x equals 6, you'll get 6 to the 6 times e to the next 6 right here. Whatever that'd be this funny thing here. Now 0 is a local min because of your left-right behavior that we talked about earlier, and by the same behavior, 6 is a local max. Number 7, we do f prime, we do f double prime. Find any c such that f double prime of c is 0. So we'll either have undulation or we'll have inflection. That c value is 1. Now, and as luck would have it, you'll check to the immediate left and check to the immediate right. Guys, pick 0.99 for the left, something very close to the left, and pick 1.01, something very close to the right. If you get up and plug them into f double prime, if your signs change, if you get a negative on one of them and a positive on the other one, that's inflection. But if your signs are the same on both of them, if your F double prime doesn't change signs, you've got an undulation point. But I think we get lucky here. We have an inflection. You'll find that F double prime does change. So, and as luck would have it, it's concave up from 1 to infinity and concave down from neg infinity to 1 in this example anyway. So find the inflection point. Well, if you plug 1 back into the original function f to get the y value, you'll get a y value of neg 5. And guys, yep, there you go. And you got to make sure, F double prime being 0 is not enough. You got to make sure that F double prime changes signs by using a test point, like 0.99 and 1.01 or something. I've got to go, guys. But this one's just going to go the same way. For concavity, you'll do the second derivative, and you'll see, you'll set it equal to 0 and see where it changes signs. It's got to change signs. But we'll write that down. Y'all have a good day, and bye now.